Now, the main thing is how to do the analysis of a continuous beam before going to design. Okay. So, analysis of continuous beam having main two approaches. Having main two approaches. One is exact method. One is exact method, and second is IS coefficient method. Okay, so these are the two main approaches for analysis of continuous beam. And in exact method, the simplest method is moment distribution method. Moment distribution method. Okay, so moment distribution method. So now I am going to tell you how exactly these two approaches are applied on a beam. Okay, so in that first I will tell you how the IS coefficient method is applied on a continuous beam for the analysis purpose. Okay, so first is the IS coefficient IS coefficient method. IS coefficient method. So IS coefficient method is given in IS 456 on page number 36. IS 456 2000 version on page number 36. Okay. On page number 36, table 12 and table 13 given, and table 12 is related to the bending moment coefficient and table 13 is related to the shear coefficients. Okay. Now, IS coefficient method, directly the coefficients are given and directly find out the bending moment at particular locations. Okay. So now I want to sketch the continuous beam. Now I want to sketch the continuous beam. Okay. So this is the continuous beam. This is the continuous beam. Okay. So this is the continuous beam. This is support A, support B, support C, support D, support E. Okay. So this is the end span. This is the end span. These are the interior spans. These are the interior spans. Okay. So this is the end support. This is the end support. So this is the next to end support. This is the next to end support. Support B is the next to end support. Support D is the next to end support. And support C is the interior support. So the table 12 is related to the moment coefficients. Table 12 is related to the, so table 12 is related to bending moment coefficients. Table 12 is related to bending moment. So directly the bending moments coefficients are given, and that coefficient you have to multiply by W into L. That coefficient you have to multiply by W into L is the load, multiplied by L is the length. That means you have to multiply by WL square as per the note given below that table 12. Now what is the span moments? Near middle of end span. So this is your end span. This is your end span. Now what is the moment? What is the moment? The moment for the bending moment coefficient for dead load is 1 by 12. 1 by 12 W dead L square plus 1 by 10 W live L square. So this is the bending moment. This is the bending moment at end span. This is the bending moment at end span. It is 1 by 12 W dead L square plus 1 by 10 W live L square. So this is the bending moment at end span. The same formula you have to use for this end span. Same formula to use for these end span. Same formula to use for the end span. Now at interior spans. So these two are the interior spans. Okay, these two are the interior spans. These two are the interior spans. So now how to find out the bending moment? The coefficients are given. The bending moment M is equal to 1 by 16. 1 by 16. It is W dead L square plus 1 by 12 W live L square. Okay, so it is clearly mentioned in this. The first coefficient is dead load and imposed load when it is fixed, and second coefficient is imposed load not fixed, that means it is the live load. Okay, the first coefficient is related to the dead load and second coefficient related to the live load. Like this you have to find out the bending moment. Like this you have to find out the bending moment. First end span, this is the formula. For interior span, this is the formula. BC and CD are the two interior spans. Now what about the support? The support moments having a negative coefficient. Negative coefficient means it having a hogging nature. It having a hogging nature. Okay. So it given bending moment coefficient at next to end support at this location. So bending moment coefficient at next to end support. Bending moment coefficient at next to end support, the bending moment M is equal to, what are the coefficient? 1 by 10 W dead L square plus 1 by 9 W live L square. So you have to find out the bending moment at this location using this formula. Okay, bending moment at next to end support. This is also next to end support. You have to apply the same formula. At this location, and if you require the bending moment at support D, you can find out using this formula. Now on interior support, bending moment at interior support. Bending moment at interior support, how it is calculated? So M is equal to 1 by 12 is the coefficient for dead load. W dead L square plus 1 by 9 is the live load. So these are the bending moment coefficients at interior span. At interior support. So use this all formula. These formulas are available on page number 36, table 12. Find out all these bending moments and analyze the structure, and using that bending moment, you have to design the section. Where WD is a dead load, and WL is the live load, isn't it? Okay, so these spans, exactly what are these spans, I will tell you when I will solve the problem. So this is the IS code coefficients related to flexure. Now I want to tell you the shear coefficients. Now I want the shear coefficients on table 13, which are available on table 13. Okay, which are available on table 13. Okay, again I want to sketch the same beam, continuous beam. These are the end support, these are the next to end support. Okay, and this is the interior support. Okay, so support A, support B, C, D and E. Okay, same thing, while calculating the force only have to multiply the load. That means these all coefficients are multiplied by W into L only. Do not multiply by L square. You have to multiply only W into L. Okay. At end support. At end, so I will write it here. At end support. At end support, that means at this support. So what is the shear force V? What is the shear force V? It is 0.4 W dead into L plus 0.45 W live into L. So this is the shear force at this location. Okay. Again, the first coefficient is related to dead load. Second coefficient is related to live load. That means you have to find out the end support shear force. Obviously, the shear force is nothing but the reaction. And if you find out the maximum reaction, for that value you have to design the shear stirrups. Okay. So at end support A, the shear coefficients are. If you want to find out the shear force at this end support, you have to apply the same formula. You have to apply the same formula. Then at next to end support, at next to end support, at next to end support, what you have to do? At next to end support, outer side. Okay, outer side coefficients are different. That is, outer side coefficients are 0.6 W dead into L plus again 0.6 W live into L. Then inner side coefficient is different. That is 0.55 W dead into L plus 0.6 W live into L. So using these two criteria, you have to find out the shear force at next to end support. Shear force at next to end support means at B and at D. One outer side criteria is given, that means upper and lower. Inner side criteria is given, okay, because the shear force is varying from down to up to down. Like that, outer side and inner side, two different coefficients are given to find out the shear force. And at all other interior supports, okay, at all others interior support, what is the formula? V is equal to, it is 0.5 W dead into L plus 0.6 W live into L. So this is the shear force at this location, interior support. At end support, you have to use this formula. At next end support, you have to use this formula. At interior support, you have to use this formula and find out the total shear force. And find out the total shear force, W dead and WD nothing but the dead load, where WD is nothing but the dead load and WL nothing but the live load. Use these all coefficients and find out the shear force. And for that maximum shear force, you have to design the shear stirrups. Okay, is it clear? Exactly what are the meaning of these spans L1, L? So I will tell you when I am going to solve the problems. Okay. Now I am going to the exact method. What exactly we have to do in exact method? Okay. In exact method, I am going to tell you the procedure of a moment distribution method. Exact method moment distribution method. Moment distribution method. Please remember that when you want to design any beam, the first requirement is bending moment and second requirement is shear force. For that bending moment and for that shear force, you have to design the beam. Okay? Bending moment for longitudinal reinforcement, that means you have to design the longitudinal reinforcement for that bending moment and you have to design the shear stress for that shear force. That's it. Finally, if you get the bending moment and if you get the shear force, use that values for design of a beam. Okay? So, exact method, what exactly you have to do in a moment distribution method? The step number one, first to find out the distribution factor. Calculate distribution factor. Simply it is called a DF. Calculate distribution factor, DF. How it is calculated? There is one small table. I will tell you. Okay. So for that we do draw one table, joint. Okay. Then I will write it. Joint. Then members going from that joint or come to meet at that joint. Then relative stiffness. It is nothing but a K. How the K is calculated? The moment of inertia divided by span. The moment of inertia divided by span, you have to find the relative stiffness. Then next is the total relative stiffness. Total K, that means summation of K. Total K, that means summation of K. And finally you get a distribution factor DF, that is K divided by summation of K. K divided by summation of K. Okay, already I have told this thing in a theory of structure, but I want to repeat it. But I will tell detailed when I am going to solve this problem. So first we have to find the distribution factor using this small table. Okay, take down the joints, then write down the list of the member from that joint. Find out the relative stiffness, moment of inertia divided by span. Okay, then total relative stiffness, total K summation of K, and finally the distribution factor is K divided by summation of K. Using this, find out the distribution factor. Second step is calculate. Fixed end moments. So we have some directly formula for the fixed end moment. Use that directly formula and find out the fixed end moment. Simply it is called FEMs. Okay. Then third, plot the distribution table. Plot distribution table and distribute the moments. So, what is the distribution table? You have to plot a distribution table like this. You have to. I want to give one small example of two span beam. Okay. So, in this place you have to put the distribution factors. In this place you have to put distribution factors. Okay. You have to put the distribution factor in this place. Then you have to put the FEMs, fixed end moments. You have to put the fixed end moment at this location, and then go for the distribution, distribution by applying some simple steps, that is releasing. Okay, second one carry over, releasing, carry over, then completion line, and addition. Completion line and addition, you have to follow 1, 2, 3, 4 steps. 1, 2, 3, 4 steps, and do the distribution in this table, and finally plot the bending moment and shear force diagram. And finally plot the bending moment diagram and shear force diagram. Bending moment diagram and shear force diagram, and using that bending moment diagram and shear force diagram, catch the peak moments and design the beam. Catch the peak moment and design the beam. But I want to remember you, these iterations are carried out till the equilibrium conditions have to satisfy. Equilibrium condition have to satisfy. Do these 4 steps, 1, 2, 3, and this is the 4th step, plotting of BM in SFD, and take the maximum shear force and bending moment, and maximum shear force and bending moment, and do the design. Okay. Now I want to tell you how to design the continuous beam. What are the different steps you have to follow for design of a continuous beam, that I want to tell you now. Now design of a continuous beam is nothing but finding the dimensions, okay, and finding the longitudinal steel for bending moment, and finding the shear reinforcement. That's it. Now what is the main requirement? What is the main required data? The required data is ultimate bending moment and ultimate shear force. The required data is ultimate bending moment and ultimate shear force, FCK and Fy. Okay. Material properties. FCK is a characteristic compressive strength of a concrete, and Fy is the yield stress of steel. Now, what you have to calculate? Required to calculate. Okay. Required to calculate. Okay. Width of the section, depth of the section. Required to calculate width of the section, depth of the section, area of a tension steel. If compression steel is required, then you have to find out, and shear reinforcement that you have to design. Okay, that means required data is ultimate bending moment, okay, then ultimate bending moment, ultimate shear force, FCK and Fy. Okay, I will continue. Now first you analyze the structure. From that analysis you take the maximum bending moment. Okay, the first step is you have to design the longitudinal reinforcement. Okay, design of longitudinal steel. Design of longitudinal steel means you have to find out the longitudinal tension steel at bottom, longitudinal tension steel at top. For that, the first requirement is bending moment. That bending moment, that maximum bending moment, you have to you have to take from the analysis, from our exact method and I-squared method, and do the further steps. Okay, in that first, take maximum bending moment. Take maximum bending moment from analysis. Okay. Step 2, calculate maximum depth. Calculate maximum depth for that bending moment. Calculate maximum depth for that bending moment using the formula MUR max is equal to RU max BD square. RU max BD square. Particularly, you have to assume the width of the section. You have to assume the width of the section in between 300 to assume width of section 200 to 400 mm. 200 to 400 mm. Okay, and find out the depth of the section. Or there is one small simple shortcut. Okay, you can put the overall depth. You can put the overall depth of the section, that is the maximum span divided by 10. Or you use this approach, or you can use this thumb criteria, that is maximum span divided by 10, maximum individual span divided by 10, and provide the overall depth. Okay, so do this, find out the width and depth of the maximum, and finally provide the steel. Okay, step number 3, provide a longitudinal tension steel by using formula. So AST is equal to 0.5 FCK divided by Fy 1 minus under root of 1 minus 4.6 bending moment mu. Okay, then FCK BD square into BD. So because you are providing the depth for the maximum bending moment, that means in all other sections, at support, at span, at interior support, at next to end support, all other locations, the beam is acting as an under reinforced section. So simply you have to use this formula. And find out the steel and provide the steel at different locations. So these are the three main steps. You have to follow while designing the beam for the flexure. Now, what about the shear reinforcement? Okay. So next is about the shear reinforcement. So we know that the shear reinforcement required a shear force. For analysis, take maximum shear force. BU max. Take maximum shear force BU max and do the steps whatever we have done in last semester in DCS 1. Same steps you have to follow and find out the stirrups. Design the stirrups. Okay. Then step 2, if you get the maximum shear force, find out the nominal shear stress. Step 2, find out the nominal shear stress. Already you know this tau b. So tau b u, ultimate nominal shear stress, tau b u is VU divided by V into D. Okay, tau V is the nominal shear stress. Okay, it is not equivalent in what we have done instead unit 1. It is normal steps that whatever we have followed in DCS 1. Okay, so tau V, then calculate same thing, then calculate tau C and tau C max from table 19 and 20 respectively. Okay, calculate tau C and tau C max from table 19 and 20 respectively from IS 456. Okay, and compare these three stresses Okay, so when tau C max is more than tau V is more than tau C, tau C max is more than tau V is more than tau C, shear reinforcement is required. Shear reinforcement is required. Shear reinforcement is required. If shear reinforcement is required, then you decide the simple form of a shear reinforcement, that is vertical stirrups. Okay, don't go for the bend up bar and incline stirrups. Shear reinforcement is required. So assume particular form. Okay, if your tau C, if your tau V is more than tau C max, if your tau V is more than tau C max, so you have to change the grade of concrete. Okay, change grade of concrete. Change grade of concrete. And if your tau C is more than, if your tau C max is maximum value, okay, if your tau C is more than tau V, if your tau C is more than tau V, design minimum shear reinforcement. Minimum shear reinforcement. Design minimum shear reinforcement. Okay, by using the page number 48, we have to design the minimum shear reinforcement. Okay, so if shear reinforcement is required, then what to do? If shear reinforcement is required, if shear reinforcement is required, what to do? So assume diameter of stirrups, proper diameter of stirrups. Assume diameter and legs of stirrups. Assume proper diameter and legs of stirrups. And how to find out the spacing? The formula is available on page number 73. The formula is available on page number 73. Okay, and calculate spacing. And calculate spacing using the formula V is equal to 0.87 Fy ASV into D divided by SV. 0.87 Fy ASV into D divided by SV. This formula is available on page number 73. So what is VUS? So VUS is the shear force for shear stirrups. Shear force for the shear stirrups. How it is calculated? So VUS is equal to total shear force minus shear force taken by the concrete. Minus shear force taken by concrete. So it is VU minus tau C BD. You do this small calculation and put this VUS in this place and find out the spacing SV. And find out the spacing SV. Already you know these things. What is ASV? ASV is the area of unshielded bar multiplied by legs. It is pi by 4 d square multiplied by legs. Pi by 4 d square multiplied by legs. Okay, do this, but the spacing should not exceed. It is on page number 48. The spacing should not exceed. Okay, it is given in IS code. The spacing should not exceed 0.75 d. Okay, maximum spacing of shear reinforcement measured along the should not exceed 0.75 d. Okay, this is the effective depth. So I will check it. It is 0.75 d. Okay, so the spacing should not exceed. Spacing should not exceed. One is 0.75 d, where d is the effective depth of the beam. Second is 300 mm. Okay, and third is minimum spacing. Third is minimum spacing, and that formula is ASB upon B into SB is equal to 0.4 divided by 0.87 Fy. Okay. Okay. ASB, already we know the meaning of ASB. SV is the spacing. Do this calculation. Find out the three values and provide the minimum of these 4. 1, 2, 3, 4. So this is the design of shear reinforcement.